In the second part of 11.1, we are going to look at permutations with restrictions and permutations with repeating items. What we have to remember is with permutations with restrictions is that we have to deal with the restrictions first. So what we are going to do is set up our blanks, decide where the restriction is, go to that blank, figure out the number of choices for that blank, and then arrange the other items around it. The type of restrictions that we are talking about here is we may want certain items in certain positions. We may want certain items to be together. We might want certain items to not be together, or we may want items to alternate. So these are the kinds of restrictions that we are going to look at in this section. Let's look at example 9. How many permutations of the letters in the word orange are formed if? First thing we are going to do is count up the number of items we have. In this example, we have 7 items. And the other thing that we always check to see is if each of those items are distinct from the others. And in this case, they are. So we have 7 distinct items. And what I mean by with distinct is I don't have any items that are identical to the other items or repeating items. So in this case, we have 7 different items. A, the first letter must be N. I'm going to draw 7 blanks to represent my 7 letters. And it says the first letter must be N. So I'm going to deal with that restriction first. And that restriction is in the first blank, the first letter. How many choices do I have for that first position? We have 1 choice. It has to be an N. Once I've put the N down, I cannot use it again. And now when I go to the other blanks that do not have restrictions, I can think about the number of choices for those ones. Since I've used the N, I have 6 choices left for the next blank, 5 choices for the next one, 4, 3, 2, and 1. Fundamental counting principle says to multiply all the numbers together, and writing in factorial form, this becomes 1 times 6 factorial, or just 6 factorial, which is 720. So there are 720 arrangements of the letters of the word oranges that begin with the letter N. Part B, the vowels must be together in the order O, A, E at the beginning of the arrangement. This question has 3 restrictions. Restriction number 1 is that the vowels have to be together. The second restriction is that the vowels have a particular order. And the third restriction is that the vowels have to be at the beginning of the arrangement. So let's deal with each of those restrictions. Starting with the vowels must be together. Anytime we have an example where items must be together, what we are going to do is we are going to take those items and put them together inside a circle, which represents that those 3 items now become a single item. So they used to be each individual units. Now we stick them together and they become 1 unit. The remaining letters, which would be R, N, G, and S, all still remain as individual units. So we no longer have 7 items that we're talking about. Now we have 5 items that we are talking about. The vowels come together to create 1 unit. The consonants are 4 individual units, so 5 items that we are arranging. That is dealing with the first restriction. We have put the vowels together. The second restriction, in the order O, A, E. So inside this big circle where I've put O, A, and E, I'm going to put equals 1. And what I'm showing there is that the number of arrangements of those vowels is 1 because we are given the specific order O, A, E. Now, so that's the second restriction taken care of. For the third restriction, the beginning of the arrangement, what I'm going to do is I'm going to draw 5 blanks. And again, I'm only drawing 5 blanks because we've gone from 7 items to 5 items because we've glued 3 of them together. In this arrangement of items, I have a restriction in the first blank because our third restriction is that the vowels must be at the beginning. So I only have one option here. It has to be the vowels. The vowels are counting as 1 unit, so 1 choice there. The remaining blanks is for the remaining letters, which are our consonants. We have no restrictions, so I can use any of the 4 consonants in the next blank. Once I put one down, I can't use it again, so 3 choices for the next blank, 2 and 1. Fundamental counting principle says to multiply all our numbers up. So we have 1, which represents the arranging of the vowels, times 1 times 4 factorial, which is the arranging of our blanks. This reduces to just 4 factorial or 24 arrangements. You will notice that that is a very small number of arrangements, but 3 restrictions here. And each of those restrictions is limiting the number of permutations, so we get a very small number. If we look at part C, we can see that there are 2 restrictions. 1, the vowels must be together, and 2, the vowels have to be in the order O, A, E. So because we have less restrictions in part C, we should see our number of permutations increase. Dealing with our first restriction, the vowels must be together, I'm going to do the same thing I do above. I'm going to take the vowels, and instead of counting as 3 individual objects, they are now counting as 1 unit. The other letters, the consonants, R, N, G, and S, are still individuals. So that's our first restriction. The vowels must be together. We've done that. They now count as 1 item. In the order O, A, E. So inside that circle where I've put O, A, and E, I'm going to write a 1 beside it, which represents the number of orders or arrangements of those vowels. And now I'm going to arrange the items. So I'm going to draw 5 blanks. We only have 5 items because the vowels are counting as 1 item. But you'll notice that in part C, that third restriction from part B is gone. So I don't have any restrictions on these blanks. That means that in that first blank, I have 5 choices. I might put one of the consonants, or I might put my group of vowels there, but I'm not told exactly where. So we have 5 choices. Once I've used one of those choices, I cannot use it again. So we have 4 choices, then 3, then 2, then 1. Fundamental counting principle says multiply all your choices together. So we have 1, which represents the order of the vowels, times 5 factorial, the order of our items, which simplifies to just 5 factorial, which gives us 120 arrangements. So as predicted, we've got more arrangements with part C than part B because we have less restrictions. Part D. In part D, we have the vowels must be together. So again, we have that same thing there, that we have to have items together, but in any order. So we only have 1 restriction with part D, and that is that the vowels have to be together. So let's do this the same as the past 2. Let's draw our circle. Let's put our vowels in that circle. They are now counting as 1 unit. The consonants are still individuals, so they get their individual units. That's our 1 restriction, that items must be together. So when I go in and look at my arrangements of O, A, and E, I have 1 order there. I have multiple orders. Since there are 3 items inside that circle, I can arrange those 3 items 3 factorial ways. Then I go ahead and arrange the 5 items that we have. Again, we have no restrictions on what order these items are going to go in. I have 5 choices for the first blank. I might use the vowels. I might use one of my individual consonants. Whatever I use, I cannot use again. 4, 3, 2, 1. Fundamental counting principle says multiply all of your choices together. This becomes 3 factorial times 5 factorial, which is 720 arrangements, which again is an increase in the number of arrangements, but it makes sense because we only have one restriction in D versus in C and B where we have multiple restrictions. So anytime you see items together, put them together in a circle, arrange the other ones in their individual circles, you'll have a limited number of items. You'll arrange the items that are inside the circle, arrange all of your items together, and multiply. E, the vowels are not all together. So what we need to do is we need to interpret what that means. Not all together means I can have some of them together. So I might have the O and the E together. I might have the E and the A together. We have lots of different options for putting the vowels together. And instead of figuring out what all the options are of having the two vowels together, we're going to come at this from kind of a backwards way. What we are going to do when we have something that says not all together, which implies that some can be, what we are going to do is we are going to take the total number of arrangements of all the letters. So we're going to find the number of all the possible arrangements. Then what we are going to do, we are going to subtract, or we are going to take out all of the arrangements that have the items all together. So we're going to subtract the arrangements with all the vowels together. By doing that, by taking all the possible arrangements and removing the arrangements where all the vowels are together, we are left with the number of arrangements where they're not all together. We are left with those that have two of the vowels together or all of them separated. But that's how we're going to come at this, because it's too much work to go at it in a forwards direction, finding all the different possibility of some of the vowels together. This is a little bit easier. Now, our total number of arrangements is the total number of arrangements with no restrictions. So we have our 7 items. We are arranging all 7. We have no restrictions. That's going to be 7 factorial. Minus the arrangements that have all of the vowels together, and specifically all of the vowels together in any order. Well, that's exactly what we found in part D. So I'm going to subtract 720, which was our answer from part D. Part D was the number of arrangements with all of the vowels together in any order. So 7 factorial minus 720. We can go to our calculator to do that. So put in your 7, math, go to that probability menu, number 4, minus 720, and then we will get our answer, 4,320. So that is the number of arrangements that have the vowels not all together. So maybe 2 together, maybe all separated, but not all of them together. And this strategy will work anytime you see not all. F. Now F looks like it's almost asking the same thing as E, but it's not. So again, we need some interpretation there. It says none of the vowels are adjacent. Now what none means is it means I can't have 2 of them together. I can't have 3 of them together. We can't have any of the vowels beside each other. So adjacent is another word for together, as is beside. So beside, adjacent, and together all mean the same thing. However, not all and none do not mean the same thing. None of the vowels can be together. Here's how we tackle that. What I'm going to do is I'm going to start then with the consonants. So I'm going to draw 4 blanks, which represents all 4 of my consonants. Now, in order for the vowels to not be together, what I need to do is I need to place them in between the consonants. So I can put them in that one in that spot, or that spot, or that spot, or that spot, or that spot. So we have 5 possible places that we can put the vowels in between the consonants, and then we guarantee that the vowels will not be together. So let's go ahead and put some numbers to this. So for the blanks for this, we've got no restrictions of what consonant goes where. So I have 4 choices for the first spot. We have 3 choices for the third spot, 2 choices for the next spot, and then 1. So our arrangements of the consonants is going to come together and be 4 factorial. Now, the arranging of the vowels. We have 5 spots that we can put those vowels in, but we only need to use 3 of them. So to calculate the number of arrangements of the vowels, we're going to write 5 spots, P, because we are arranging 3 of the vowels. So 4 factorial and 5 permute 3. And because we're using the fundamental counting principle, we are going to multiply in between those 2. So to the calculator we go. For math, go to the probability. Number 4, there's our 4 factorial, times, put our n value in, go to that probability menu again. Number 2, 5 permute 3, and our answer 1,440. That's the number of arrangements that have none of the vowels together. They are in between the consonants. So read the questions carefully. Not all is different than none, and we have 2 different strategies that we use for both of them. Part G, the vowels and the consonants alternate. So we have to use a little bit of logic for this one. I'm going to go ahead and draw the 7 blanks because it doesn't say anything about items being together or none of the vowels being together. It says they alternate. Now, we have fewer vowels than consonants. So in this example, we have to start with a consonant and then a vowel, and then a consonant, and then a vowel, and then a consonant, and then a vowel, and then a consonant. We cannot start with a vowel because if we do, watch what happens. We would have vowel, consonant, vowel, consonant, vowel, consonant, but then I'd have a consonant left over, which would mean that we do not alternate at the end. So you have to sort of plan it out a little bit to see what works. And in this case, it only works to start with a consonant. We are not restricted as to which vowel or consonant we have to use in a particular order. So we're going to start with 4 choices of consonants. Then I have 3 vowels to choose from, so 3 choices of vowel. For the second consonant, I've already used up 1 in the first blank, so I only have 3 choices for this blank. For this vowel, I've already used 1 up in the second blank, so 2 choices here. For the third consonant, I only have 2 choices left. For the third vowel, I only have 1 choice left. And for the last consonant, 1 choice. Fundamental counting principle says to multiply those together. And even though this is in kind of a different order, we could actually write this as 4 factorial, 4, 3, 2, 1, which represents your consonants, times 3 factorial, 3 times 2 times 1, which represents your vowels. So 4 factorial times 3 factorial, we can go to our calculator and do that. 4, math, go to probability, number 4 times 3, math, go across to probability, go ahead and put in number 2, and then we would put in, oops, sorry, we would just need 3 factorial. Let's try, well, we know what it is. 4 factorial is 24, 3 factorial is 6, and we get 144 items there. Moving on, let's look at permutations with identical items. So in all of the above examples, in any of the ones we've done before with permutations, Our group of n items contained no repetitions. Each item was different or distinct from every other item. But what happens if there are duplications of items? So the quick example that I like to look at is looking at the three letters M, O, and M. And let's sort of similar to T, O, and M, which we looked at in the first part of the 11.1 notes, we arrange those three letters. This one has a repeating letter. It has identical M's. So one of the arrangements would be M, O, and M. I can leave the M in front and I can reverse the order of the M and the O. So there's another permutation there. And then I could put the O in front and the M's behind. Interchanging the M's in any of these three arrangements does not create a new permutation. They are identical. So instead of getting the 6 expected arrangements that we would get, we're only getting 3 arrangements or 3 permutations. Now, keep in mind, we are still arranging the 3 items. So we are still starting with 3 factorial arrangements. Arranging 3 items, we can only use each of them once, 3 factorial. But because the rearranging of the M's does not work, does not create a new permutation, what we do is we divide, so take away 2 factorial, and that 2 factorial is the arrangements of the 2 identical M's. 3 factorial divided by 2 factorial gives us our 3 arrangements. So that is how we are going to deal with identical items. We are going to divide by the number of those items arranging, so n fact or the factorial. Looking here, if there are n identical items, if there are identical items in our group of n options, the number of permutations can be found by n factorial times a factorial, b factorial, c factorial. So there is how we're going to do it. The important part there is that dividing in the bottom by the arrangements of the repeating items. Now, we won't always have 3 things that repeat. So just like the quick example we just did, I only have 2 M's that repeat. So I'm only going to divide by the 2 factorial. But if we have multiple items that repeat, we have to divide by their arrangements in the bottom. Let's look at example 10. How many permutations are there of the letters in each word? So we're going to start off the same way we would with any other permutations questions, because right now we know there's going to be identical items, but on a test or a quiz or a worksheet, you always have to be on the lookout for identical items. So we're always going to start by counting the number of items we have and then checking to see if there are repeating items or if all of the items are distinct. In Vancouver, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 items or 9 letters that we are arranging. And then when we go in to see if we have any repeating items, we can see that we do. I have a V here and a V here. So we have 2 V's. None of the other letters are repetitions. So now we can go ahead and we can arrange. We start with the fact that we have 9 items. We are using all 9. We have no restrictions. So there are 9 factorial ways of arranging those items. However, when I interchange or arrange the V's, that does not create a new arrangement. So I'm going to divide by 2 factorial. We can put that into our calculator to get the number. So 9, math, arrow across, and then choose number 4. Okay, number 4, 9 factorial, and we are going to divide by 2, same thing. And I'm also going to show you an alternate way to put this into your calculator that's going to help us when we have more items that repeat. We can also hit our alpha button and then y equals, and then choose number 1. And what this does is it puts it in that fraction form. This is really going to help us when we have multiple repeating items. So I would do the same thing. In the numerator, we're going to put that 9 factorial and then arrow down to the bottom and we can put in the 2 factorial. So it doesn't help us a whole lot in this one, but it will help us in some of our other examples. So we get 181,440 different arrangements. Part B, we have the letters in the word mathematical, counting up the number of letters we have here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 items here. And check to see if we have any repetitions, and we have a few here. I can see we have 2 M's. I can see we have 3 A's. And we also have 2 T's. So to start, I start with the 12 items. We are arranging all 12 of them, and we have no restrictions. So there are 12 factorial ways of arranging those 12 items. However, we need to divide by 2 factorial, which represents the rearranging of our M's. I also need to divide by 3 factorial, the rearranging of the A's, and 2 factorial, the rearranging of the T's, because rearranging those letters does not create a new permutation because they are identical. So going to the calculator, here's where that fraction form is really going to help us, because then we don't need to worry about putting brackets around the bottom. If your calculator does not have this function of putting it in that fraction form, then just make sure that when you put it in your calculator, you put brackets around your denominator. So to the calculator we go. I'm going to go alpha y equals number 1 and put it in that fraction form. We have 12 factorial on the bottom. So we're going to go to that probability menu, number 4, arrow down, and in the bottom, we have 2 factorial. We have 3 factorial. And we have 2 factorial again. We could also just calculate what 2 factorial times 3 factorial times 2 factorial is and divide by that number. Lots of different options for you for actually putting it in the calculator. We do get a fairly large number here, but keep in mind that 12 factorial is a fairly large number in and of itself. So in this, we have 19,958,400. So a relatively large number there. 19,900 and let's go back here really quick, 58,400. Okay, in example 11, we are again going to have a word that has repeating letters, but now we're going to put it together with what we talked about in a previous example with restrictions. Example 11, use the letters of the word mummies to find the number of permutations. Okay, so before we start, count up our number of items. We have 1, 2, 3, 4, 5, 6, 7 items here. And we should notice that we have 3 M's. So we have some identical items here. What I'm going to do is right off the bat here, I'm going to take care of the fact that we have those 3 M's by going to each part of this question and writing divide by 3 factorial, divide by 3 factorial. Same thing with part C and part D. I'm going to put in there divide by 3 factorial. And by doing that, I've taken care of the repetition part of this question. And now what I can do is just deal with my 7 items and the arranging of the 7 items using the restrictions I've given. I have the divide by 3 factorial there, which will remind me to do that at the end, and then I'm fine with this question. Part A, there are no restrictions. We have 7 items. We are arranging all 7 with no restrictions. That means I can arrange them 7 factorial ways. We do have to divide by 3 factorial to take care of those 3 M's. So let's go to our calculator and find that. 7 factorial is 5,040. Oops. Divided by 3 factorial, which is 6. And so we get 840 arrangements for that one. All right, the arrangement must begin with a vowel. So I'm going to draw my 7 blanks. 1, 2, 3, 4, 5, 6, 7. We are talking about the starting of the arrangement. That's where my restriction is. So that's where we're going to start. And it has to start with a vowel. We have 3 vowels in this question. We have U, I, and E, which means I have 3 choices for that first position. Once I've placed one of the vowels, I cannot use it again. Now those other 2 vowels plus all of the other letters come together, which means we have 6 items that we can use for the next blank. Once I put that item down, I can't use it again. So 5 choices for the next one. 4, 3, 2, and 1. Fundamental counting principle says to multiply those all together. So simplifying, what we get here is 3 times 6 factorial, but we have to divide by 3 factorial because of having the 3 identical m's. So the nice part of having the 3 factorial already written there is sometimes what ends up happening is you do all your arrangements and you get so caught up in how to do the arrangements that you forget about dividing out your repeating letters. So it's nice to have that from the very beginning, and then you won't forget to have it. So going to the calculator here, we have 3 times 6 factorial is 720, divided by 3 factorial, which is 6, and that gives us 360 arrangements there. Next up, part C. The arrangement begins with 2 m's. So I'm going to draw my 7 blanks again. We are looking at the beginning part of this arrangement, and we are looking at the first 2 blanks since it says we want to begin with the 2 m's. So in the first blank, we have 3 m's total to choose from. So that means I have 3 choices for that first blank. And once I put an m down, I cannot use it again. That means we have 2 choices for the next one out of the 2 m's. The remaining blanks have no restrictions, so the remaining m is going to join up with all the other letters, meaning we have 5 choices for the third blank, then 4, then 3, then 2, then 1. We are going to multiply all those choices together. And so what we get here is 3 times 2 times 5 factorial, but we can't forget to divide by 3 factorial because rearranging the m's does not give us a new permutation. So putting this into the, and again, it's nice to have that 3 factorial sitting there to remind us to do that. So 3 times 2 is 6, times 5 factorial is 120. Again, dividing by 6, which represents that 3 factorial, and that gives us 120. So you can see it speeds up on the calculator a little bit when you know what some of the factorials are. So knowing that 6 factorial is 720, knowing that 5 factorial is 120, you'll start to recognize the numbers and it gets easier to put it into the calculator. So for this one, we have 120 arrangements that are possible. Now, part D says the arrangement begins with exactly 2 m's. And you might be thinking, well, we just did that. We did that in part C. But we do have a different word in there. We have that word exactly. And that's going to have an effect on our number of arrangements because it's actually another restriction. And you might be surprised about where that restriction is. So I'm going to draw the 7 blanks. Now, we know it begins with the 2 m's, so we know we have a restriction on those 2. This has to be an m, this has to be an m. But because we have that word exactly, we also have a restriction on the third blank. This third blank cannot be an m. The reason is if we have m's in the first 2 blanks and then an m in the third blank, that would mean that we are starting with 3 m's. 3 is not exactly 2. So that word exactly means we have a restriction on that third blank. It cannot be an M. And what sometimes helps with this kind of question is to write the word that we are dealing with and cross letters off as we use it. So the first choice, we have 3 choices. It has to be an M. We've got 3 M's to choose from. So I'm going to cross out the first M because I put 1 down. Now I've got 2 M's left to choose from. So I've got 2 choices there, and I'm going to cross that out. Now, this third blank cannot be an M. So I can use the U, the I, the E, and the S, which means we have 4 choices for that third blank. Now, let's say that I put the U down. So I can't use the U in the next blank. I can use the I, the E, the S, and now I can use that M here. So again, we're going to have 4 choices, and it's because we've used one of the other letters, but the M comes back into play. So 4 choices, then 3, then 2, then 1. So sometimes it is handy to write the word beside, cross things off as you use it, and then you can see the number of choices that you have left. Fundamental counting principle says to multiply all of those together. Here's what we get when we simplify. We have 3 times 2 times 4 times 4 factorial, but we can't forget to divide by 3 factorial. We still have those 3 repeating M's that we need to divide out because rearranging them is not creating a new permutation. So again, super nice that we've written that at the very beginning. As soon as we recognize that we had repeaters, we wrote it in every part. And now all we have to worry about is our restrictions. And then we have the reminder at the end to divide by 3 factorial. So we have 3 times 2 times 4 times 4 factorial. 4 factorial is 24. And then we are going to divide by 6, which is the 3 factorial. So just 96 arrangements for that one. Okay, and you can again see the number of permutations reducing with each step because we have more restrictions. And that's how we deal with having repeating letters. Example 12 looks very different than any of the examples we've done so far. We don't have any items or letters that we repeat. This is a pathways question. So we're still counting, but what we are doing is counting the number of paths from A to B, and we put this condition on it that in this case, the movements can only be down or to the right. In any of these pathways questions, when we are moving from point A to point B, we always have the condition that we have to move closer to our endpoints. In this case, that's B. And the reason we say that we can't backtrack is if we could, then there would be an infinite number of paths that we could take because we could move away from A and then go back towards A and then get a little bit closer to B and then come back. So to eliminate that, we say we have to move closer to B. So one way we could do this, which is not a recommended way, but one way that we could do this is we could draw the paths. So one possible path from A to B would be go all the way across and then go down to B. So that's one possible path that we could take. Another path that we could take is we could still go across, but maybe not as far, and then go down and then across and then down to B. So that would be a second path. We could show a third path. Maybe instead of going across, maybe instead we want to start by going down and then over to B. So that would show 3 paths right there. Now, I can tell right away that's not going to be super efficient. I don't want to draw all the possible paths and then count them all up. So that's not a method that we're going to use. So here's what we're going to do instead. We're going to recognize that we can only move down and to the right. So on this grid, what I'm going to show is that no matter what path we take, we have to go 4 blocks to the right, and we have to go 2 blocks down. But we can do that in any order. We don't have to go all the way to the right and down. We could go 3 over, 1 down, 1 to the right, 1 down. We can do this RRRDD in any order. Well, as soon as we say that, that means we are arranging those letters. So what we do is we can actually take those letters, remove them from the grid, and just imagine that this was our question. we have these 6 letters. I want to arrange these 6 letters with no restrictions. So we have 6 items that we are arranging. However, we have 4 identical R's and we have 2 identical D's. So from above, we know how to arrange something with repeating or identical items. The 6 items can be then arranged 6 factorial ways, but we must divide by 4 factorial, which represents the rearranging of the R's, and 2 factorial, which represents the arranging of the D's. So instead of thinking of it as a grid question, think of it as a word question. We just have kind of a weird looking word. Count up your number of items, divide by your repeating items. So from here, we can go ahead and put this into the calculator. Let's hit our alpha button and our y equals to get it in that fraction form. 720 is 6 factorial. In the bottom, 4 factorial is 24 times the 2 factorial is 2, and we get 15. So what that means is there are 15 paths from A to B. Let's look at part B. We're going to approach this in the exact same way. No matter how I get from A to B, we are going to have to go 3 blocks to the right, and we are going to have to go 2 blocks down, but we can do that in any order. So if we take this off the grid, we have 3 R's and 4 D's, which is 7 items, but we have repeating letters. We have the 3 R's and the 4 D's. So arranging the 7 items with no restrictions, 7 factorial, divided by 3 factorial, 4 factorial, which would be our arrangements of the R's and the D's. So going to our calculator, we've got 7 factorial. Actually, let's put this in fraction form, alpha y equals, and then number 1. In the numerator, 7 factorial, so 5,040 in the numerator. And in the denominator, we have 4 factorial, which is 24, times our 3 factorial, which is 6, and that gives us 35. So there are 35 pathways, in this case, from A to B. So looking at part C, it's a little bit different. We notice that we have to get closer from A to the corner and then from the corner to B, still only moving closer to B. So we do need to divide this up into 2 grids. I'm going to look at grid number 1 and then at grid number 2, finding the number of pathways from A to the corner and then finding the number of pathways from the corner to B. So here's grid 1, here's grid 2. In grid number 1, we have to go 2 values to the right and we have to go 1 unit down. So for that one, that's RRD that we are arranging. That's 3 items that we are arranging 3 factorial ways, but because we have identical R's, divided by 2 factorial. In the second grid, a little bit different. In that one, we have to go 2 to the right and 4 down, or 3 down. So in the second grid, we are looking at R, R, D, 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 which is 5 items that we are arranging 5 factorial ways, but we must divide by 2 factorial for the repeating R's and 3 factorial for the repeating downwards D. We have to get through grid number 1 and grid number 2. So we are going to multiply in between. You can also think of it as fundamental counting principle, the number of pathways through the second one, the number of pathways through the second one, and then we multiply. So we go ahead and put this into the calculator, put it in that fraction form. So alpha y equals number 1. For the first one in the numerator, we had 3 factorial, which is 6, divided by 2 factorial, which is 2. We're going to multiply that by fraction form one more time. And in the numerator here, we had the 5 factorial, which is 120, divided by 3 factorial, which is 6, and 2 factorial, which is 2. And so our answer there ends up being 30. 30 pathways from A to B in those two grids. And that finishes up the notes for 11.1, Fundamental Counting Principle and Permutations. Next up, we are going to look at 11.2, Combinations.